all to our webinar today titled Report Interpretation, Understanding Wear Metal Results. My name is Ashley Stromack. I'm your host today, and I'm a Customer Engagement Specialist here at Test Oil. A couple of things before we get started. The first thing is everyone is on mute, and that is because we are recording the presentation today. So to ensure a high-quality recording, everyone's on mute, not to interfere with the audio. We do encourage you to ask questions, though. There is a questions bar in the GoToMeeting application. So if you can type in there and we can answer those questions either during, after the presentation, or through email later on. The recording will be emailed to everybody, and it will be attached with a survey, and that will go out later this afternoon. So I believe that's all the housekeeping, so let's get started. Our presenter today is Evan Zabowski. Evan is the Senior Technical Advisor at Test Oil. He is a certified lubrication specialist with extensive experience training tradesmen and professionals in a variety of fields, including lubrication fundamentals, contamination control, condition monitoring, and used oil analysis. Evan is heavily involved with STLE. He's been a member for over 18 years, and he's served the last 8 years as editor of TLT magazine. He also recently joined the board of directors and previously served as the editor of the Basic Handbook of Lubrication, 3rd edition. So Evan, if you're ready, let's get started.
Great, thank you, Ashley. So for today's presentation, we're going to begin with a discussion about the test behind wear metals before we get into understanding all the different wear metal results. So what I'd like to start off with is just straight from the ASTM method for elemental spectroscopy, what is the intended scope of the test, and go through the significance and the principle and so on. Now the scope of testing is that with elemental spectroscopy, we're not just measuring wear metals, but we're also measuring additive elements and contaminants, and those will be actually addressed in some upcoming webinars. The significance of measuring all these different parameters is it gives you a good indication if you've got the correct fluid in the application, if the machine that it's in is undergoing any type of normal or even abnormal wear, and as well helps identify to some extent what might be the causes of the wear, namely contamination. So the basic principle of elemental spectroscopy is that a sample is diluted and then injected into a plasma. And you can see the plasma pictured here. The sample is injected from the bottom up into the plasma. Now, for lack of a better word, it's burned. It's really ionized, but any material that's placed into that plasma, which is sitting at about 10,000 degrees Kelvin, so as hot as the surface of the sun, will ionize in that plasma. What happens is that when the material ionizes, it emits light, and every element on the periodic table produces different spectra of light. And what we're going to do with this instrument is measure the intensity of the different wavelengths of light, and that gives us, in the end, an elemental concentration. What is intended by understanding this part of the testing is that this test does not measure for Babbitt or brass. What it measures is copper, lead, tin, elements like that. So we have to interpret from the proportionality and ratios of the different elements what type of material or alloy we might think it can be attributed to. But first and foremost, we must understand this test is only measuring for elements. That's why it's called elemental spectroscopy. Just to give you a little bit of a visual of 3 different wear metals, I've chosen aluminum, tin, and lead and shown how if you look at them, you can find at least one wavelength that's been depicted that is unique to that particular element. With tin and lead, you can see there's a lot more potential for some overlaps, so we're always being conscientious of this and selecting a particular wavelength that will not interfere with another wavelength from a different element. So the fundamental thing that we have to understand is that this is an elemental concentration. The second fundamental aspect of this test that must be understood is that when the sample is injected into the plasma that we were looking at here, the sort of oval circular thing off to the right of the plasma is essentially the window that is looking at the plasma, and anything introduced into that plasma must burn up completely within that window. If it does not, then it escapes complete detection. So as such, the second fundamental thing about this test is that it is known to accurately measure particles within the 0 to 5 micron range. Beyond 5 microns, up to about 10, using a round number, the accuracy drops off significantly, and beyond that approximate 10 micron value, this test does not measure the particle accurately. Now, some people will state that the test is blind. I say it's essentially blind. The particle is measured, but it's not measured to quite the same extent that it should normally be measured. The analogy I like to use is, imagine if we were quantifying a meteor shower. So if we went out into the night sky and looked up and saw meteors hitting the atmosphere, you would see streaks of light as they burn up across the atmosphere. If we recorded the times that each individual meteor was streaking across the sky, we could find a way of approximating the size of the meteor, meaning longer streaks of light must be larger meteors because it took more time to burn up. However, if you think about standing in something like, say, an ice fishing shack, looking up through a skylight, a 1 square foot window straight up into the night sky, and now try and imagine how much of the meteor shower can you see through that small window? Not as much. And could you differentiate small particles from large particles? Well, essentially, hopefully you're seeing where this analogy is going. And no, even if a large particle, a large meteor, streaked past that window, because you're looking at such a narrow point of it, you would perceive it as a smaller meteor because you would not know that it started streaking before it hit the window, and you wouldn't know if it was continuing to streak after it had gone past the window. That's the same with this test. It's not that it does not see large particles at all, it's simply that it doesn't measure them as accurately, doesn't quantify them to be as high. As such, this fundamental aspect of the test identifies to us a severe limitation to the test, in so much that if you can see the particle in the bottle, meaning that you've taken a sample of oil and it is glittering, it looks like metallic paint, essentially this test could give you near zero values for wear metals. And you might be confused as to, why couldn't they be detected? It's all the nature of the test. Now, going back to my earlier comment about picking individual wavelengths, that is what helps prevent cross-elemental interferences. But some of the other interferences that are not as easily dealt with is that the sample must be able to be dissolved in whatever solvent we're using before we introduce it into the instrument. So as such, there are certain types of materials, be they oddball synthetic oils, or for that matter, some grease samples, that don't function as easily in this test as do normal lubricants. So we have to switch up the solvents and recalibrate the instrument if we're going to measure those ones. Another interference is water content. It's not that water does not ionize within the plasma, but it causes the plasma to sputter. So if you go back to my analogy about standing in an ice fishing shack and trying to quantify meteors simply by looking straight up through a skylight, imagine if somebody was on the outside of the shack shaking it while you were inside there. You can see how your measurements might not be as accurate. So when we get a high water content sample, and if the plasma sputters, we know the results will be of lower accuracy. Just as an illustrative point, spectrometry does have a loss of accuracy at larger particle sizes, but luckily there's a crossover with large particle detection methods such as analytical ferrography or wear particle concentration that can easily bridge that gap. So it's not that all oil analysis testing cannot measure large particles. It's simply that this elemental spectroscopy will miss out on some of them. So saying that, there's only one last real point to make about the test, and that is the precision and bias statements for elemental spectroscopy. Now, when ASTM develops a method and they set the precision and bias statements, they use two different terms. They use repeatability and reproducibility. Now, repeatability is when they're referring to testing the exact same sample with the same method, but in this case, you're in the same lab with the same operator on the same day, essentially. So we call this the as close as possible result. Generally speaking, it's when you analyze the same sample exactly twice in a row, one right after the other. How close could those two results ever be to each other? The term reproducibility, however, maintains that you're using the same method on the same sample, but in this case, it could be sent to a different laboratory, or it might be rerun using a different analyst, or possibly even a different piece of equipment. So in this case, we call this the real-world comparison. How close could you realistically ever expect two results to be? Now, when ASTM defines these, it's to provide the precision and bias statements for the method, knowing how accurate can this method ever be. When they do these statements, they typically follow up with a statement saying it shall only be exceeded 1 case in 20, meaning a 95% confidence rate. So 95 out of 100 samples should be within the values I'm about to show you. 5 out of 100 could fall outside of those values, and yet the method is still considered to be valid. One little extra note I'd like to provide to you is that what we're going to sort of take away from the values I'm about to show you is that though reproducibility is really defining running the exact same sample 2 different times on possibly 2 different instruments, I'd like to equate reproducibility to what happens if we take a sample from a machine and achieve a value, and then a month later take a second sample from the exact same machine and analyze it. Assuming that there were no changes to that machine, no changes to that oil in that time frame, essentially then reproducibility would show you, well, how close could those 2 results ever be to each other? And that's just assuming no change. So what this is going to do by showing you these numbers is give you an idea as to what we would call how much wiggle room do we have when we interpret the results. So here are the 2 charts. Repeatability is on the left, reproducibility is on the right, and you will notice that they show you at different concentrations for different elements. Now, if you pick something relatively common like iron at 100 parts per million, you notice on the repeatability chart it has a value of 5. This is the allowable variance between 2 measurements. It's not a plus or minus value, it's an allowable variance. So it can vary by up to 5 parts per million at a concentration of 100 parts per million. That is how close we're expecting a sample to be analyzed twice in a row. If you look to the right-hand chart and look at the reproducibility, however, iron at 100 parts per million now has a reproducibility of 21 parts per million. Meaning that if we took the exact same sample and analyzed it twice, but happened to do it on different instruments or different days or with different operators, we would expect the results to vary by up to 21 parts per million. So what I'm trying to illustrate here is that when you look at consecutive samples, arguably, to a point, you can use the reproducibility values as an idea and an indicator of how much deviation should you expect from any 2 results, assuming there's no changes, which of course you know there's going to be some change. So what I'm driving home here is that a few parts per million deviation from one result to the next is actually well within the error of the method, the noise on the instrument. Another thing I like to point out while we're looking at the tables like these is just to define what is exactly a part per million. 1 part per million is 1 in a million. But what we fail to understand is that 1 part per million requires the same amount of material to generate 1 part in a million, whether it is an increase from, say, 1 ppm to 3 ppm, or whether it's from 11 ppm to 13 ppm, or whether it's from 101 to 103 ppm. But a lot of people will take that small increase at a low level and think of it as significant because, as an example, 1 going to 3 is a 200% increase. But 101 going to 103 is only a 2% increase. Yet in both cases, it took the exact same amount of material to achieve that value. So however you want to look at it, the big takeaway at this moment in time is that 1 or 2 parts per million generally is very insignificant. Unless the trend has always been low and it suddenly deviates higher, 1 or 2 parts per million change from one sample to the next is usually insignificant. Now, for the sake of this webinar, we're going to go through all the wear metals that are tested via elemental spectroscopy. Some of the later webinars will cover the additives and contaminants. So I'll go through them in the order that you see on the left-hand side here. So starting with iron, the most common cause for iron to be present in a used oil sample is simply that steel, which is made up of iron and other elements, is one of the more common materials to use in the manufacture of machine parts. So iron on its own doesn't necessarily isolate what part is wearing. What we have to look at is what is it also increasing alongside with. Now, when you see a proportional increase of iron and some of those other metals, then generally you can attribute that to being an alloy. So then you'd have to ask yourself what parts might be made with that alloy. When you see disproportional increases, meaning that the softer metals tend to increase at a faster rate than the iron levels increase, that would indicate that you have 2 parts rubbing, meshing, sliding across each other, and that will help narrow down your choice of which parts are wearing. Now, what about iron appearing that might not be due to wear metals? If you see a sample and iron is increasing, but no other wear metals may be increasing significantly at the time, yet you note an increase in calcium and magnesium as well. A common go-to for folks when they see calcium and magnesium increasing is to assume hard water contamination. And that certainly may be a source. But in conjunction with iron, rather than assuming that the iron is rust due to water ingression, one of the other things I like to point out, because it's relatively common in the industry, is that any form of oil absorbent that's clay-based uses a clay called Fuller's earth, or what most of us know as kitty litter. And it is a magnesium and calcium-based clay. It has some iron in it as a contaminant. That's what gives it the sort of orange color that it often has. And this type of material is very small. It will float through the atmosphere relatively easily, ingress through most breathers, caps, whatnot. And when it gets into the system, it is an abrasive particle. It will lead to future wear. And as I indicate here, it generally does increase the particle count. So if you work at a site that you know uses this product, and especially when you use it liberally around pieces of equipment, it would not be uncommon to see increases in iron due to the use of this product and its ingression into the system, rather than assuming that the iron is directly wear material from parts within the machine. A pitfall I like to point out with looking at iron is that iron might not always be attributed to a wear mechanism in terms of physical, abrasive, or adhesive type wear. It might be more of a chemical wear, which would be corrosion. So if you know you've got a high humidity atmosphere, or if the machine happens to sit idle for extended periods of time, it is possible that parts within the machine will corrode, and that when brought into service and lubricant circulates over these parts and some of them start interfering, rubbing against each other, those rust particles will come off and they will show up in the oil analysis results. So when we do get a spike in iron and only iron, we can attribute that at times to just being a type of rust rather than a true physical, like I said, abrasive or adhesive wear. Now moving along the list to copper, copper can be found in a number of different parts. Typically it's associated with brass or bronze parts, or what we tend to call yellow metals, which may not be in the primary wearing parts, but could be in things such as bearing cages. So what we look for with copper is it increasing proportionally with other metals like lead and tin? If so, that generally indicates a brass or bronze alloy. If there's a disproportional increase of copper with other metals like lead and tin, often that's attributed to Babbitt bearings. Now there will be times when copper increases on its own. It will not be in conjunction with other metals, and it doesn't seem to align with your thoughts that it is a wear particle. In cases like this, a couple of the choices that we have is anytime we install, as an example, a new cooler using copper tubing, brand new copper, when it's shiny, does need to oxidize and form that dull protective oxidative layer. This generally takes upwards of 2 months to form, and in that time, that oxide layer may leach into the oil. So copper will appear in the oil, but it's not necessarily a sign of wear. It's not really corrosion. It's not actually a problem. And after you've changed the oil, it likely won't return. So if you see that anomalous high copper during the first couple months of service after a new cooler has been installed or a new component has been brought online, you could attribute it to the cooler. Another source, though, would be anti-seize products. One of the more predominant brands out there that obviously has copper in it would be called Copper Coat. And Copper Coat anti-seize has particles of copper contained within the anti-seize compound. And if you so much as use the anti-seize compound on even a drain plug, some of the excess might leach into the system and dissolve into the oil. By itself, it usually does not cause any harm, but it may increase the particle count slightly. So if you're looking for an explanation as to why is copper there and no other metals seem to be present, these two make some pretty natural choices. One last choice, though, occurs during the use of EP oils. When we use extreme pressure products, there are some of them which are not very friendly towards the yellow metals. In terms of EP additive chemistry, one of the more predominant and popular types of EP additives is a sulfur-phosphorus additive. Now, sulfur can take on two different forms. It can be reactive or it can be non-reactive. And when we use a reactive sulfur with the sulfur-phosphorus extreme pressure additive, it will aggressively attack yellow metals. It's going after the copper. So the picture you see here is a gear tooth with pitting that is not aligning itself with the pitch line on the gear teeth, so you know that's not rolling contact fatigue, but it is actually a chemical, an aggressive type of corrosion. So this is a case where we have used the wrong type of EP additive in a yellow metal application. Generally, you would know that this would occur if you see that your additive elements are phosphorus and not much else. In the world of additive chemistries, we typically group them into about 3 categories. Anti-wear being the first one, which has both phosphorus and zinc at relatively equal concentrations. EP, which typically only has phosphorus if it's got anything visible. And then R and O, which has no phosphorus and no zinc, generally nothing else. So R and O oils tend to look like a bunch of zeros across the board. EP oils tend to look like phosphorus, maybe a little bit of calcium, but AW oils can have phosphorus and zinc and then any number of other additives depending on what type of fluid it happens to be. So when we're using an oil, if it's not identified within its product name as EP, we can still make a reasonable determination based off the phosphorus and zinc values if it's using an EP additive chemistry. Now, something to note about copper in terms of the pitfalls is that when we have brass and bronze parts, sometimes in cases like overloaded gears, we might be tearing the metals off so rapidly under such abnormal wear conditions that the particles are too large for detection. So I always try and point out that if you're trending wear metals over time and the trending is slowly increasing, and then suddenly stabilizes, and then for the next bunch of samples doesn't increase, one might assume that the wear has stopped. I try and assume that the wear has actually progressed beyond normal wear into abnormal wear until I can prove otherwise. Sort of the flip side to that is if you only take samples at drain and you have a consistent level of a wear metal like copper, and then suddenly in the next sample you don't have any copper, the supposition is, well, things must have gotten better. As I always like to joke, well, maybe the part that was wearing is no longer present. Right? Maybe it's not able to be worn anymore. So again, unless I can prove otherwise, I'm going to assume something negative, like the particle size has gotten too large for detection, or that the wearing that was occurring is no longer wearing because the part is no longer present or interacting the way it should be. Any supposition centered around filtration, though, must understand that, again, this test is accurately measuring particles in that 0 to 5 micron range. So unless we're filtering down to less than 5 microns, filtration will have next to no effect on the levels that we're measuring. So don't always assume that, well, the filters must have removed it, because not a lot of people use less than 5 micron filters in most operating systems under full flow conditions. Next on the list is lead. Lead is commonly found in Babbitt materials, tends to be the top layer, so often you'll see lead and tin together. Eventually you might hit other metals. That indicates that you've got a multi-layered journal bearing, and once you're into the lower layers, that tends to be the tipping point where you will condemn the bearing and schedule a bearing change. But where else could lead come from? Again, if we're using coolers, when the cooling tubes are installed, they tend to be soldered in place. That solder does contain lead. It's generally mixed with tin, and it will leach into the oil if we've got elevated acid numbers. By itself, this is not generally a problem. So even if we see an elevated acid number and we see lead and tin starting to increase, just because we've got some leaching doesn't mean any significant damage is occurring. It's more a trigger for us to say we need to change or at least bleed and feed this oil and reduce the acid number to slow down the rate of this type of corrosion. Should also be noted that lead is pretty commonly found in anti-seize compounds as well. So if we know we're using them, we know that work has been done recently on the component. If we see that initial spike in lead and then it doesn't move after that, we can attribute it to this type of ingression. And again, this is not likely to cause any long-term problems. It just is present. The pitfall with lead, as I've just given you the two examples, not all lead is from a mechanical wear. It's not always a journal bearing wear that's producing the lead. Sometimes it's the leaching, sometimes it's the anti-seize compounds. We can live with these to a point as long as we're able to address why they got there and know what we can do to prevent them from increasing significantly. Aluminum, on the other hand, is one of those elements that is often attributed to wear that is generally and not necessarily always from wear. When we think of a component like an engine and we know that the block is made out of aluminum, some folks are pretty quick to say, well, that's where the aluminum is coming from. However, engine blocks are not designed to wear. Most engine blocks are lined with other parts to prevent the wear of the block itself. For two reasons. One, the block is a lot more expensive to change out, but two, when we use materials like aluminum, these tend to be too soft to withstand significant wear. So when we think of aluminum, ask yourself if it's an actually oil-wetted and wearing part, because aluminum can be used in a lot of different components that are not meant to necessarily be wearing parts, and sometimes they're not even oil-wetted. They're just lightweight parts used as casings outside of other things. So where we would see aluminum as a wear metal would be if we had a true aluminum part in a wearing type application, and I'm suggesting things like thrust washers and bushings seem like a pretty reasonable example. When we think of an aluminum piston, on the other hand, the piston isn't necessarily going to wear, the rings are going to wear. The rings are usually made of other metals. So just to give a couple examples. So if aluminum isn't a wear metal, why then do we see it so frequently in oil samples? Well, if you've ever heard the expression, red sky at night, sailor's delight, red sky at morning, sailor take warning, you've actually been told very indirectly why that might be. When we have a sunset that is not our normal yellow, orange type color, when it starts to go into the glorious reds and purples, what's changing is the atmospheric contamination, and that's what's changing the wavelengths of light that bounce off the atmosphere. Now, normally in the atmosphere, we always have dust. Dust on its own is generally silicon dioxide. It's a breakdown product of quartz, sand. When the color of the sunset or sunrise changes, the contaminant has gone from dust to dirt. Now, a lot of folks might think dust and dirt are the same, but dirt is actually aluminum silicate. It has about a 3-to-1 ratio of silicon to aluminum. So when we see a different color sunrise or sunset, where that saying comes from is that dust is in the atmosphere normally. Dirt, a much larger particle, doesn't tend to stay in the atmosphere as easily. So when we do get it in the atmosphere, it must have taken more extreme conditions, must have taken higher winds, and that's where the saying comes from. In our lubricated components, what this means is that we don't have just normal airborne dust getting in, we now have large dirt particles getting in. So this might indicate to us a failure of the breather, a cap that's been left off, a dipstick that's fallen out, whatever it might be, but this is a larger particle requiring a bigger entry point. So it either took more extreme conditions or we've got less protection. So when we see aluminum, one of the first things we should always look for is what's the level of silicon. If the level of silicon is approximately 3 or 4 times the level of aluminum, you can make a fairly safe assumption that the aluminum you're seeing is from dirt and not from any type of metal product. One of the only other exceptions I can think of where you might find aluminum that's not necessarily from a wear metal would be for those working in particularly power plant applications that are using activated alumina, one of the brand names of that being Selexor. It is a sodium and aluminum based product. It will escape its filter housing to some degree, and that powder that escapes will produce some level of sodium and aluminum in the oil. Now, generally, it's not very harmful in the short term. In the long term, it can help to produce some metal salts within the system, which is not good. But if you've got decent particulate filtration on the oil, you'll probably strip most of it back out. It just takes time. The pitfall with aluminum is that aluminum is not necessarily a wear metal. Aluminum might actually be the cause behind the wear metals that you're seeing because it may be an indicator of dirt ingression. And dirt, like I said, is a much larger particle than dust. It's also more abrasive. It will cause more damage. So whenever we see aluminum and we see that silicon ratio kicking in, start checking for points of ingression. Make sure your breathers are installed correctly, make sure everything's buttoned up tight, caps are back on, so on and so forth. If your system is simply protected with an OEM style breather, like the one you can see in the picture there, generally speaking, those do a very poor job of preventing dust and dirt from getting in. So the recommendation then would be to upgrade the breather, and that would help prevent the entry of more aluminum in the future. Tin, as we've already covered, is generally part of the Babbitt material. So tin tends to occur with the lead. As we see other metals like copper appear, that indicates a lower level of the Babbitt bearing kicking in. If you see tin absolutely by itself, particularly on a new component, sometimes it's used as a bit of an overlay, and it has been known to be used in piston overlays. So those using engines might see tin just on the first few samples, and then it levels off, and after an oil change goes away. Tin also appears as solder, like we talked about with lead. But one of the other sources of tin that does escape some people's notice is that the use of polyester type synthetic fluids often contain a couple hundred, 300 parts per million tin, and that is part of the additive that's used as a catalyst within the manufacture of the fluid. So it doesn't do anything in the fluid once it's been manufactured, but it does remain there. So it's a level that shouldn't change over time. It will neither go up nor down, but it's not there to do anything. It's not set to serve any purpose. So without a baseline sample, you might be surprised by some very high levels of tin in the oil. Pitfall with tin, again, echoing what we said about lead, sometimes it's a corrosion product. It's not necessarily mechanical wear, it's more of a chemical wear. But the other side of it too is what size is the particle, right? If we get the particle size is increasing due to the severity of the wear, it is possible to see a drop-off or a leveling off of the wear metal values. Now, nickel is not commonly found in too many components, but when it is, usually it has something to do with bearings. In the case of journal bearings, it may be one of the intermediate layers, one of the lower layers, which could be an indication of the time to change the bearing. In rolling element bearings, though, sometimes it is visible only during break-in. So knowing what is typical for that application certainly helps. If you suspect that it is just for break-in, again, within the first couple months, it will probably increase, and then after an oil change, you won't see it again for a long time. Where else you'll see nickel? Going back to our anti-seize compounds, I mean, it's right in the name. You will see products that have nickel specified as what is sort of the primary ingredient in them. If you're using these and have any excess entering the oil system, you will see it. Now, the pitfalls with nickel have a lot more to do with the correlations. When you see nickel on its own, that often indicates a break-in. If you see nickel and chrome together, generally speaking, those indicate some sort of coating, as they tend to be used together for coating of parts like shafts and valves. If you see nickel, chromium, and iron, and now adding in the iron, increasing proportionally, this now suggests an alloy wear, because there's lots of steel that's made with both nickel and chrome as much lower levels of alloy material than the iron content. So always look at the nickel and what else it seems to be matching up with. It's a very important part of doing the proper interpretation of all the various wear metals, is not so much isolating each element and seeing if it's increasing, but seeing what it's increasing alongside, and if that increase is remaining proportional or if it's disproportional. Sticking with that theme, if we talk about chromium next, as we've already stated, it is used in the plating or coating of parts. So when we see the proportional increase of chromium and iron, that is an alloy. If we see a disproportional increase of chromium and iron, but it may be proportional with nickel or silicon, that's what's giving us an idea that it's actually the coating on the part. So this helps identify if we've got coating versus the subpart being worn, or just identifying what part is wearing. One of the other sources of chromium, though, would be from stainless steel. So you will see still a proportional increase with iron, but in this case, if you're looking at a system and saying, well, it doesn't have any steel alloy parts, where could it be coming from? It might just be coming from the lubrication piping. So when we see the proportional increase, and I've given the ratios here vary anywhere from 1 to 10 to 1 to 4, and that's in terms of there's more iron than chromium, this would indicate to us that we've probably got some stainless steel erosion. If there's an increase in acid number alongside of this, then we've probably got corrosion. It's actually chemical wear at this point. So the pitfalls with chromium remain very much the same as the ones for nickel. Right? Always looking for the correlations. As we already said, the chromium and nickel together, probably just coating. When we see chromium, nickel, and iron, that's what suggests it's an alloy. If it's just chromium and iron, there is no nickel, then that suggests it's probably stainless steel, a different alloy. Now, titanium tends to be a very rare element. Not a lot of people see titanium in their systems, but those that do usually have a pretty short list of where to find the parts. If we see titanium and iron increasing proportionally, then it's probably a type of iron alloy. If the part is predominantly titanium or some titanium alloy, what it's usually alloyed with is aluminum and vanadium. So if you've got a sample and it has high titanium and high vanadium in particular, and it's from an engine, almost guaranteed that the predominant source of the wear metals is going to be the connecting rods. Where it gets tricky is that some engines will run different fuels, and certain fuels may contain vanadium as a bit of an after effect from the crude oil refining. And there are some oils today that are containing titanium additives. So what was once a very telltale combination in a very specific application is now being masked by sort of oddball combinations of the right oil with the right fuel will produce the same results on a report as a particular part that's wearing. So again, why I stress at the beginning that one of the fundamental things about this test is that it is measuring the elements and the elements only, is if we measure titanium and we measure vanadium, we can't tell if those are coming from an actual metal part or if they're coming from organometallic additives found in oils and residual metals found in crude oil. Titanium also presents another interesting sort of case as to where else could it come from. If it's not a wear metal, where might titanium come from? And it has certainly shown up after overhauls and other recent PM type work. And people often get very confused as to why might titanium suddenly appear when it has never appeared before, and especially if they can't think of any logical source of titanium parts. But where it can come from is from knowing that titanium dioxide is actually a pretty widely used product. It's what makes sunscreen work. It's what brightens dairy products so they look whiter. It's what makes bright paint bright and what makes white paint white. All are from titanium dioxide. So when a machinist uses layout fluid, as you see in the picture there, just to check gear mesh or whatever it is, as that paint wears off, it will enter the lubricant. Now, it's not going to cause any harm, but it will be present. So until the oil is changed after the use of this layout fluid, there will be higher levels of titanium than would be normally expected. If the machine has actually been painted, especially when they use aerosol type paints or if there's any overspray onto the lubricated side of the component, then that paint may dissolve or wear off slowly and enter the oil. Again, as paint or any form of aerosol type paint, it's not an issue. It just provides you with an explanation as to why is the titanium present. Now, one note about titanium, because certainly I've read a fair number of tables and charts recommending potential sources of elements. I always question when people put things on lists like turbine blades. It's often listed as a source of titanium. While I don't disagree that turbine blades are made from titanium, I would ask, are they oil wetted? Are they wearing? How would turbine blade material get into the lubricant system? So try not to fall prey to examples like this where different wear elements may be listed as sources, but then you have to ask yourself, how could that possibly get into my lubricant? If there isn't a logical path, then you can eliminate that as a potential source. And that's why I provided you with the paint example, because it's a far more logical source, even though it seems like it's way out in left field, it occurs actually very frequently. And there are people who are very, very confused when titanium suddenly appears because titanium is not commonly found. So they're always looking for that explanation. Now, moving along our list of vanadium. Vanadium, not very common at all as well. Tends to be just as rare as titanium. But it is used as an alloy in some steels, so always look for that proportional increase with iron and vanadium. When it's a disproportional increase, it's probably a coating, and generally speaking, with most coatings, chromium is the predominant element that you'll see there. So whether it's chromium with nickel or chromium with vanadium, these tend to be indications of coatings. Now, as I already mentioned, if you happen to be running an engine application, there is the possibility of vanadium appearing, and it's from the fuel. Bunker C is a type of fuel that's made from crude oil, where the crude oil is not refined very well. It's kind of a poorer quality type fuel. And if the crude happens to come from the Caribbean or Mexico area, it tends to have much, much higher vanadium values than it does in the rest of North America. So for folks operating pieces of equipment that run Bunker C, which tends to be mostly marine-based, you will see elevated levels of vanadium, and they may be on their own. They may correlate with a number of other metals that are found on the oil analysis report. And as long as they correlate closely with the other metals, the vanadium can be assumed to be largely from the fuel and not from an actual wearing part. Now, silver, the last one on our list, is very unique. Silver is not used in too many applications, partly due to cost, partly due to it's only used where its specific properties are needed. So it has been used in overlay for bearings in EMD locomotive engines, and it is used in some aviation applications. One of the big reasons that it's used is it has a run-dry capability, meaning it's possible to use this metal and prevent significant wear even if it's running dry. So that's why it tends to be used in the aviation industry. If you ever run out of oil, you'd kind of like your rotating parts to be able to go a few extra turns without having any issues. So it gives some run-dry capabilities in that aspect. Now, if silver is not found as a wear metal, where else could it be found? We can go right back to our solder example. There are some solders that do contain silver. Now, they're not very common, but it should be noted that it is possible. So if you see your silver increasing with tin and with lead, then it is possible that the silver's coming from there, and generally if you've got an increase in acid number, then you know it's probably leaching in. The downside to using silver parts, though, is that they have a bad synergy that occurs with zinc additized oils. So as much as the sulfur, reactive sulfur from EP additives didn't like copper, zinc really doesn't like silver. It will react strongly with silver parts. So when we do have a EMD locomotive type engine or an aviation application using silver parts, it's always recommended that we use a zinc-free formulation. Now, zinc is commonly found as an anti-wear additive in many types of hydraulic and engine oils, so it becomes a pretty popular choice, but we can use tricresyl phosphate instead, and that will provide the same type of anti-wear protection without giving us the potential for the silver corrosion. So saying all that, we've reached the end of our list of what we wanted to cover today. Certainly, if you've got any questions, please use the question or the chat windows off to the right-hand side here. If you don't want to ask your questions now and want to send me a question later, I've thrown up my email address there so you've got it. But I will turn it back over to Ashley now to see if anyone has submitted any questions that we can answer while we're still live.
All right. Thank you, Evan. That was a great presentation. Like you said, if you have any questions, please feel free to use that chat window, and we can get those answered for you now. All right. Okay, the first question is regarding the different element sizes and the limitations on the spec. What other tests do you recommend to capture those larger size particles?
Well, as we saw on that one slide, I'll zip right back to it just so you can see it in writing too. When we are concerned that there may be larger particles present in the oil than are being detected by spectroscopy, definitely analytical ferrography will give us a broad spectrum of all the larger particles, be they wear metals, contaminants. Wear particle concentration, on the other hand, is just ferromagnetic particles. So it obviously focuses on ferrous, iron type parts, and it can provide no information on anything else. Or you can do something simple like a patch. That always works too. It doesn't give us as strong of a qualification as to what things are because they just look, like silvery. Whether they're ferrous or not, we can't tell directly from a patch. But if you're wondering if there are larger particles, it's a pretty quick way of determining that they're present. Analytical ferrography just offers you, sort of the most forensic type analysis where it not only identifies the size, it can identify the alloy and even the wear mechanism that caused it to be there. So those would be the three that I would go with. Another choice that you always have is EDXRF, energy dispersive X-ray fluorescence. It is a form of spectroscopy similar to what I've described here in that it does measure elemental concentration. It does do about 20 different elements simultaneously. The difference is that rather than ionizing it in a plasma, we're exciting it using X-rays, and it is not limited to particle size at all. So it will give us everything from the near zero up to pretty much any size you want. So that's another choice, but again, it's still just an elemental concentration.
Okay, I have another question here, and it's regarding the level of water in the oil sample. If there's a maximum number where you're still able to receive the results, and if there's a way to prepare the sample to minimize the interferences.
Certainly that depends on the type of fluid. There's no set value as to when too much water becomes a problem. Some fluids like water glycols contain 46% water, to 50% water, routinely, and they can be measured via elemental spectroscopy. Whereas there's other samples that are not meant to have water in them, and concentrations of a couple thousand parts per million can skew the results significantly. So generally what is done is, selecting a solvent that when you do the dilution before the sample is introduced, it helps negate these effects. And this is, one of the reasons that we do apply an internal standard to that solvent to confirm the dilution is consistent. If the sample wants to separate readily from the diluent, you'll catch that on your internal standard. You'll know that it's not dissolving properly, and that may be partly because of the water interference. The other way would simply be to run the sample twice. If you can't reproduce the values, that's a pretty strong indicator that the water contamination is significant enough to affect the accuracy of the result, because it doesn't give a constant bias. When water does skew the result, it skews it very abnormally. That's kind of your two-sided answer there. So no, there's not a set level. There's not a cutoff point where you would know definitively it's going to cause a problem. But like I said, you can avoid a lot of that by choosing an appropriate solvent. And if you're ever in doubt, run it in duplicate, and you'll have a pretty solid answer.
All right, I got one more question here, and it's asking if we'll be able to download the slides later, or if there's going to be a copy of the presentation available.
Yeah, and like you said, certainly there's the recording of this webinar that's available, and I will make the slides available to Ashley. So if you have any desire for them, we'll be able to provide them to you.
All right, I don't have any other questions, so I think we're all set for now, but if anybody does come up with any questions later on, please feel free to email Evan directly, or you can email anyone here at Test Oil, and we can get those questions answered for you. Evan, thank you again for presenting that. That was great information, and have a great day, everyone.